Hi guys, hope all doing good. Today in this video session we will start probability and statistics. Before going to the engineering level, let's discuss some basics from intermediate, because for those who come through intermediate to engineering it's easy for them to understand directly, but for those who come through diploma they find it little difficult to directly understand the engineering concepts. So let's discuss few intermediate concepts. Coming to the first definition, it is our sample space. The sample space is denoted by S, and it is the set of all possible outcomes of an experiment. Experiment can be rolling a die, or measuring a height, or weight, or amount of matter, or tossing a coin, or anything can be an experiment. Outcome, all the possible outcomes. Not, we don't want only 2 or 3 outcomes. We want all the outcomes of that experiment. Say, if tossing a coin, then all the possible outcomes. When one coin is tossed, we can get only one head or one tail. So this set is called sample space for the experiment tossing of coin. For rolling a die, the sample space, when one die is rolled, then we can get 1, 2, 3, 4, 5 or 6. Among the 6 digits, we can get any number of dots. You may be familiar with this dice. Who has played with this Ludo, they will be familiar with dice. So on each side we will having these dots. Number of dots means that number. 1 means 1. 3 dots means number 3. So whichever is on the top surface, that number is the outcome of the rolling of die. So here we got 1. In this case it is the answer. In some other case we may get 3. In some other case we can get 4. That way we can get all the possible outcomes are 6. These numbers 1, 2, 3, 4, 5 and 6. So this is one thing. And same measuring weights. Measuring weight of 9th class students is an experiment that are being conducted to understand who is obese, who is slim, who is normal, everything. So say they have given maximum limit of or maximum weight of any person in the 9th class is say 60 kg and minimum weight is 40 kg. So we cannot say some person may get 40.5 kg, some can say 55.555 kg. So in that way, any outcome can come that is continuous. So in the sample space will be the total interval between 40 kg and 60 kg. In between that, it can be any value depending on the person's weight. So we cannot say we will get 41 only. We cannot describe 41, 42, 43. Weights can even be 41 point something, 42 point something. So we cannot count it. We can only measure it. So depending on the outcomes, this sample space can be described or classified into discrete or continuous. For those experiments whose outcomes are clearly countable, it may be finite or it may be infinite number of outcomes. Here in this case it is finite number. We can directly see them, only limited number of outcomes. So it is finite. In some cases we can get infinite number of solutions or outcomes also. But if we can count each and every one, then it is discrete sample space. If we cannot count, we can measure, but it can be any real value between this 40 and 60 given interval. If the outcome can assume there is no restriction for it, can assume any value between this one, then it is continuous sample space. So that is how our discrete and continuous sample space. Now after sample space discussions, we will go for permutations and combinations, which is regarding the arrangement of given items or objects or entities. And one more thing, in sample space, we have got some 1, 2, 3, 4, 5, and 6, say in rolling of a die, each element or each entity is called an element or sample point. Even and any subset 1, 2, say 1, say 1, 2, 3, anything, any subset of this, which constitutes any of these elements, even null set, this each and every subset of this sample space, we will call it as an event. How this event, for example, say in rolling of a die, our experiment is rolling of a die, but our desired output is we will get an odd number. Then we get odd number chances are 1, 3 and 5. So this is a subset of this sample space. So this is an event. Our event is, our experiment is rolling a die. Our event is getting an odd number, and getting an odd number, that event is a subset 1, 3 and 5. This is among this. So even null set, which is 0 and a no output, is also a subset of this. So in this way we call it as this is an event, or getting an even number, or getting a co-prime numbers. Anything, event can be anything which is subset of sample space. Now there are n objects, n different objects taking R at a time. If we want to arrange, then total number of arrangements possible then the total number of arrangements possible is, I am calling here arrangements, not combinations. Combinations will be a different criteria. Arrangements, sequence is very important. When I say number of arrangements, sequence is important. Sequence in the sense, in what order, sequence or order. So total number of sequences or orders or arrangements possible equals to NPR, which is equal to n factorial by r factorial into, n factorial by n minus r factorial. So this is NPR, total number of arrangements possible. Now, if in the if n objects are given, in that some n1 objects are alike, and then again some another n2 objects are alike, and again some n3 objects are alike, and remaining objects are different. These all n1, n2, n3 and remaining objects are different, they are distinct. So if constituting all these elements, we will get n objects. So if such is the case, total number of arrangements with all these n objects possible is, so that is total number of permutations, nothing but total arrangements, total number of arrangements possible equals to n factorial for all the objects. Since n1 are alike, so we will get n1 factorial into n2 factorial into n3 factorial. Okay, so it will be clear like this: n1 factorial into n2 factorial into n3 factorial. So total number of arrangements will be n factorial into n1 factorial into n2 factorial into n3 factorial. I said arrangements again. So arrangements, in arrangements sequence is important. Now when coming to combinations, this is permutation. You can write heading as permutations. This is everything is about permutations. Now when coming to combination, in combination we just group the entities together. We don't again arrange. That arrangement is their concern. We don't concern about arrangement. We just concern about grouping. So when we are concerned about groups, that part we will call it as a combinations. So when sequence is not of prime importance, heading will be combinations. For n given objects, say they are different, all are different, n different objects, we want to group n different objects taking r at a time, taking r objects at a time, r objects at a time. So say we are having some 3 apples or 3 apples, 4 bananas, 5 oranges or some set. We want to group them such that we have 3 fruits. One fruit will be apple, one fruit will be banana and another fruit will be orange. So we just want to group orange, banana and apple. We are not concerned orange is first or apple is first or banana is first. Anything can be first, anything can be second, but we want all these 3, 1 apple, 1 banana and 1 orange, group of 3 as a set. So only just grouping is important. That time how many number of combinations is possible? Such questions come under combinations. In this case, if n are different objects, total n are different objects, then r at a time we want to take, then grouping, number of groupings or number of combinations possible is NCR, which is equal to n factorial divided by r factorial into n minus r factorial. With this we will get number of groups, and each group are objects. So when we want arrangements, that is sequence is important. In each group as r objects are there, each group again we can have r factorial ways of arrangements. Number of sequences can be r factorial. So total number of arrangements can be, since these many groups are possible, combinations are possible, and in each group r factorial ways of sequences are possible, total number of arrangements will be r factorial into n factorial divided by r factorial into n minus r factorial, which is equals to NPR, which we have already assumed or already discussed earlier. So when it comes to total number of arrangements, we will take NPR, which is n factorial by n minus r factorial. When we are grouping, only sequence is not important, only grouping the things, then it is NCR, n factorial by r factorial into n minus r factorial. Okay, so hope the thing is clear by this. Now coming to examples. First one, find the number of permutations. Number of permutations, which means sequencing, is important. Number of arrangements, total number of permutations of all the letters of this word committee. Okay, so when going to solution, first let us count total number of elements in it. So committee, COMMITTEE, n equals to total number of elements equals to 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Okay. Now, similar kind of alike elements. 2 n's are there. N1 equal to alike elements. N1 equal to 2. Again, 2 t's are there. N2 equal to 2. 2 e's are there. N3 equal to 2. So 2 e's, 2 t's, 2 m's. 2 elements alike, 2 t's alike, 2 elements, 2 e's alike. So we have that for arranging, having total array number of permutations, we have formula n factorial divided by n1 factorial into n2 factorial into n3 factorial. Okay, so which is equal to 9 factorial divided by 2 factorial into 2 factorial into 2 factorial. So from which we will get as 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1 total divided by 1 into 2 into 1 into 2 into 1 into 2. Okay, so this 2 and 2 cancelled. Again, this 2 2's are cancelled and this 2 is cancelled. When we multiply 9 into 8 into 7 into 6 into 5 into 3, we will get the answer as 45360. So you can check that later. So going to the next answer, next example. Now the second example given is from the 6 engineers and 5 architects, a committee is to be formed, a group has to be formed having 3 engineers and 2 architects. So our group has total 5 members, 3 engineers and 2 architects. This we have to select from 6 engineers and 5 architects. So how many such combinations are possible? Because in 6 engineers we can choose 3 engineers in some different kind of ways with combination formula. In the same way, from 5 architects we have to choose 2 architects. We can choose any 2 architects. So he is asking how many different combinations are possible. With the first condition is there is no restriction. We have only given thing is 6 engineers, 5 architects. So we have to choose 3 engineers, 2 architects. There is no other restrictions. Second is among the 6 engineers, there are 2 particular engineers must be included. We don't have any chance. So the questionnaire, whoever is asking will mention these 2 particular engineers has to be there. So that is this case. So we can have only option to choose from rest of the 4 engineers and remaining 1 engineer. Okay, we will solve it. So first, when there is no restriction, we have 6 engineers. From 6 engineers we have freedom to choose. And how many we have to choose? 3 engineers to be chosen. Then number of ways to choose them is NCR. Here 6. N is 6. CR is 3. 3 at a time we are taking in 6 engineers. 6 is C3. Okay. Now there are 5 architects. So we need 2 architects to be chosen. So number of ways for architect choosing is 5C2. So total number of combinations possible to form the given 5-member committees selection of engineers into selection criteria for architects, that is 6C3 into 5C2. If we saw 6C3, we will get 6 into, I will write it here, 6 into 5 into 4 into 3 into 2 into 1 divided by 1 into 2 into 3, which is 3 factorial, into 6 minus 3 factorial, which is again 1 into 2 into 3. So 6, so it is 20, 5 into 4, 20, and into, that is 6C3. Again for 5C2 when we count we will get 10. So 6C3 into 5C2, which is total equal to 200. Okay, so 20 into 10, 200. Now coming to case 2. In case 2 it has given that 2 particular engineers are already included. That means they are selected. We can do nothing about it. So our requirement is 3 engineers and 2 are already he is selecting for us. Then we need 1 engineer to choose from how many? Out of 6 engineers, 2 are already selected, fixed. So we are remaining 4 are there. So from 4 engineers. So from 4 engineers, we have to choose 1 engineer. Architects, there is no restriction. So we can, out of 5 architects, we can choose any 2 architects. So 2 architects to be chosen. From 5 architects. Okay. So combining these two, total number of combinations possible will be, out of 4 we can choose any one, into out of 5 we can choose any 2. So 5C2. Here we have to understand that AND is given. So if 6 engineers are there and 5 architects are there, so when we are choosing any 3 and we are choosing any 2, so depending on which 2 we are choosing and which 3 we are choosing, internally again there will be combinations. So don't confuse that 4C1 plus 5C2. We have to multiply because it will become as a tabular format. So it will take very long time, 20 to 30 minutes to solve this one question. So to avoid that, we use these formulas. Actually, you can link that way also. First we choose these 3, these 2. With that one combination. Again for these 3, next 2. For these 3, next 2. So in that way, again, these 3 now we will change first, second, instead of first, second time we will choose first, second and fourth engineer. Next time we will choose first, second and fifth. Next first, second and sixth. In that way, different combinations of 3 engineers and different combinations of 2 engineers can be possible. Collecting all them, total number of combinations can be given by this multiplication into formula when AND is coming. You have to remember that. So depending on the question, you have to apply mind sometimes. So 4C1 into 5C2. 4C1 we have 4 factorial divided by 1 factorial into 4 minus 1, which is 3 factorial, into 5 factorial divided by 5C2, means 2 factorial into 5 minus 2, which is 3 factorial, which is equals to 4 factorial by 3 factorial, which is nothing but 4, into 5C2 we have discussed 10. So total number of combinations possible is 40. So hope this sum is clear for you all. So let's go to next concept. So coming to few of definitions, exhaustive events, which is nothing but we can consider it as a sample space as well, because it is a set of events that include all the possible events, or set of elements that include all the possible events. So for example, tossing a coin can have either head as a result or a tail as a result, but there is no other result. So head and tail, when we form as a set, the two events together form as exhaustive events. Now mutually exclusive events. Here it means that when one event is occurring, it eliminates the occurrence of all other events. For example, when we are tossing a coin, either head falls or tail falls. When head falls, there is no chance that tail falls. And when we get tail, there is no head. It is never possible in general circumstances that both head and tail will fall at once. Only one of them falls. When one of them falls, other cannot fall. So occurrence of one event eliminates occurrence of other event, or equally likely events. So when there are some 2 or 3 or 4 or any number of outcomes possible for given experiment, so we cannot say that a particular event can occur more times than other. I mean, there is no preference. We cannot give any particular preference to one event. Every event can happen has same preference, equal preference. Then they are all together called as equally likely, which means one event can't be expected to happen in preference to another. That means all are equally preferable. We cannot say one event is preferred to another event. So when we cannot discretely say that give any preference to any particular events, then that when preference for every event is equal, then it is equally likely event. Now suppose there is an event A in a sample space which can happen. Event A is possible to happen, or success of A can happen in m ways, or m combination, whatever it is, m ways, and failure of event can happen in n ways. Means A possibility, occurrence possibility is m ways, failure which is not occurring possibility is n ways, then odds in favor. In favor means how many times it is possible to how many times it is not possible. Odds in favor is ratio of number of ways it is possible to number of ways it is not possible. When it is against, odds against an event, when it is against, which is not possible will come in the numerator, and which is possible will come in the denominator. So in favor, odds in favor, events success rate divided by events failure rate. When odds against event, events fail, against means failure, we want failure, odds against event. So event failure ways divided by number of ways it is possible or success. So hope this concept is also clear for you all. Now coming to definition of probability, we can give it in two different ways. One is a classical one which we can find in every book, which is if in a sample space there are n equally likely possibilities. That is, we cannot say first one is possible or second one is more possible or third one is more possible. All have equal chances to get outcome. That is, if there are n equally likely possibilities of which one must occur, an event A has to occur, must occur, and for that event A, yes is regarded as favorable cases or success ways, then probability of that event A is given by P of A equal to S divided by N. N is sample space, number of objects or entities in sample space, S is success ways. Okay, frequency interpretation. In terms of frequencies, if you want, when the data becomes continuous, we call it as we talk in terms of frequencies, because discretely we cannot talk 1, 2, 3 like that. So when we are taking a number line, any point on the number line can be an outcome. For example, measuring a weight, 5 kg, 5.1 kg, 5.111, anything can. So there is a continuity is there, and number of experiments also can be many when in a long run of repeated experiments. So as n, number of experiment n tends to infinity, out of that for a particular event A, if S is the success rate, then as n tends to infinity, this S by n ratio gives the probability. So probability of an event equal to proportion of times the event would occur. S times is the success rate, so S times it would occur in a long run of repeated experiments. Number of experiments or number of results are given by n. So if that experiments are repeated continuously for a long time, then n tends to infinity. So now infinite number of experiments or outcomes. In the example 3, he is asking what is the probability that in a leap year selected at random will contain 53 Sundays. Okay. So we can choose any leap year at random. We will not say it is 2016 or it is 2000. It can be any leap year. In any given leap year, there are 366 days. Okay. Out of this, we have 52 complete weeks. So 52 are complete weeks means 52 Sundays are confirmed. Exists. So what we want is 53 Sundays. So one more Sunday is required. One more Sunday is required. 52 complete weeks means 364 days. We can do per week 7 days. 52 into 7, 7 2 are 14, 1, 7, 5, 35 plus 1, 36. 364 days. So out of 366, 364 means 2 extra days are there. Days in a leap year. So these 2 extra days can be consecutively. 365th day, 367th day. It can be, possibilities are there. Monday, Tuesday, Wednesday, and Thursday, Thursday and Friday, Friday and Saturday, Saturday and Sunday, and Sunday, Monday. So these 2 consecutive days can be any of these 7 possibilities. Again, next is Monday and Tuesday, which is already there. Again, cycle will repeat. So total number of possibilities. Total possibilities 7. Out of this, we need one more Sunday, 53rd Sunday. The 50 extra Sunday is possible in this case and this case. So 2 possibilities. For success rate, S is 2. So probability of 53 Sundays. Our event is 53 Sundays and its success rate is 2 divided by total number of possibilities. S by n equals to 2 by 7. This is the probability. This is our answer. Hope this example is clear for you all. Now coming to the next example, example 4. A box contains 5 red and 10 black balls. Of these 15 balls, 5 plus 10, 15, 8 balls are taken and placed in another box. So what is the probability that latter, means second box, contains 2 red and 6 balls? So when we are taking 8 balls from these 15 balls, he is asking the probability that out of those 8, 2 are red and 6 are black. So when we find total number of possibilities, for total 8 balls chosen, so there are no restrictions, total outcomes possible when we are drawing 8 balls from total 15 5 plus 10, 15 balls is total 15C8. We are taking 8 balls, combination of a different balls in combination, taking 8 at a time. Out of total 15 balls is 5 plus 10 C8, which is 15C8. Okay, that is combination total n equal to total number of chances possible. Out of that, success rate. What is success? Success is the possibility of our event. What is our event? That out of these 8 selected, 2 must be red and 6 must be black. Okay. So, how many are there? 5 red are there. Out of that, maximum 2 possibilities possible in 5C2 ways. And 10 black balls are there. Out of that, how many? We have to choose 6 must be black. Means 2 red and 6 black. So 5C2 for red into 10C6 for black. So 2 out of 5 we can choose any 2 red. Out of 10 we can choose any 6. At random, when we are taking 8 balls, we can get any 2 balls out of 5, any 6 balls out of 9. This is chance of success. So S equal to, S means for 2 red and 6 black balls. Success S equal to 5C2 into 10C6. So for that, probability is S by N, which is equal to 5C2 into 10C6 divided by 15C8. So from this, if we expand, we will get 5C2 means, so when we solve 5C2 into 10C6 by 15C8, 5C2 we have already calculated in the earlier examples that 5C2 is 10. Now 10C6 is 10 factorial divided by 6 factorial into 10 minus 6, which is 4 factorial. So 10 we can write as 1 into 2 into 3 into so on into 6 into 7 into 8 into 9 into 10. So 6 factorial is 1, 2, 3, 4 into 4 into 5 into 6. Up to 6 it is cancelled. Remaining here is 7 into 8 into 9 into 10 divided by 4 factorial. So 7 into 8 into 9 into 10 divided by 1 into 2 into 3 into 4. So 4 2s are 8, 3 3s are 9. So which is equal to 7 3 is 21, 210. So 210 into 10 divided by 15C8. So when we try to solve 15C8, we will get a similar way as earlier. 15 into 14 into 13 into 12 into 11 into 10 into 9 into 8 into 7 into everything whatever remaining is there, that is cancelled by 8 factorial in the denominator, that remaining part, into 15 minus 8 is 7 factorial. So this is the remaining. So 7 factorial is 1 into 2 into 3 into 4 into 5 into 6 into 7. So again we have to solve that as well. So 7 2s are 14, 3 4s are 12, and 5 2s are 10, and 2 3s are, and 3 3s are. So denominator everything is cancelled. In the numerator we are having 15 into 13 into 11 into 3. So 15 into 15 into 11, 15 into 11, 165 into 13. So 3 5s are 15, 1 3 6 are 18, 19, 3 1s are 3, 4, 165. So 5, 14, 11, 2, 2 1 4 5. This again into 3, 15. So this we can write as 2 1 4. Otherwise here itself we can write it as 15 into 13 into 11 into 3. Okay, so 210. 3 into 70. 5 3s are 5 2s are. Okay, so we get as 270s 140 divided by 33 into 3 into 13, 39 into 11. Which is 429. So answer is 140 divided by 429. So hope the calculations and everything are clear. Earlier we have already discussed the definition for experiment. So we can call it as a random experiment also when it is the experiments are conducted under same situations. Now coming to axioms of probability, first one is probability of any event of the sample space A. If S is the sample space, in that any event A, there are several events A, B, C and so on, any event A, any A or B or anything, every probability always lies within the bounds of 0 and 1. It cannot be greater than 1, it cannot be less than 0. It is between 0 and 1. And for all the events of sample space A1, A2, A3 so on, if we sum up the probabilities of every event, then summation of all the probabilities of the events of sample space is 1. Next one is, if A and B are mutually exclusive, earlier we discussed that for mutually exclusive events, A and B, the two events cannot occur together. If one event occurs, other cannot occur. So, in that case, probability is either one of occurs. I am not saying both occurs. In general, addition rule is that probability for either of A or B, union means or. If either A or B to occur is P of A, means probability of event A to occur plus probability of event B to occur minus probability of both the events to occur together. So, but as given events are mutually exclusive, that means both cannot occur together, which means P of A intersection B is 0, which implies from the third axiom we will get probability of either of A or B to occur, P of A union B equal to P of A plus P of B. So this is the three axioms of probabilities. Now coming to complement concept, when occurrence of an event we term it as A, then not occurring of event A is called A complement. That means except A, if anything else happens, that is A complement. So for probability that A never occurs, A complement is 1 minus P of A. 1 is total probability minus total probability of sample space is always 1 sigma T. An earlier axiom we have read, second axiom. So 1 minus probability of A to occur. 1 minus probability of A to occur is probability of A to never occur. So P of A complement equals to 1 minus P of A. Now independent events, occurrence or failure, either success or failure of one event do not affect other event, occurrence or failure, then those two events are called independent events. Now coming to conditional probability, there are two events A and B in the sample space. It is not always compulsory that they are independent. Sometimes they may be dependent. For example, if B occurs, among that A probability of A can depend on occurrence of B or failure of B. So in that cases, we derive the concept of conditional probability, where we mention it by P of A by B, which is probability of A given B. That means the question, he already mentions what is the probability of B, and then he asks us to find if it is dependent. If A and B are dependent, then what is the probability of A when B has already occurred? When first B is occurring already, then if A has to occur, then what is that probability? That is conditional probability. If they both are independent events, then if A and B are independent events, then P of A by B equals P of A means whether P of B is anything, that is doesn't matter P of A. A is not affected by B's occurrence or failure. So in that special case, P of A by B equal to P of A or P of B by A equal to P of B. In the denominator, whichever is there, that occurs first, and whichever is on the numerator, that occurs later, afterwards. So if they are independent, denominator we can neglect. If they are dependent, then a different case comes. So that we can understand from multiplication of probability law. Generally, P of, in general case where we cannot know, we don't know whether A and B are independent or not. They may be dependent, they may be independent. So general formula for P of A by B is P of A intersection B, both of A and B to occur, divided by probability of B to occur. Means when already he has given that B has already occurred and its probability is something, then if we are going to calculate probability of A and B both to occur, when the ratio is taken, that gives probability of A taken B or given B. And similarly, P of B by A equal to P of A intersection B divided by P of A. Remember, whichever is in the denominator, that will be here also, that will be in the denominator. That's events probability will be in the denominator. So this is the case. So multiplication law, here it is division, you may confuse why it is division. Actually next step is the multiplication law. From this we can write P of probability of A intersection B, both A and B to occur, equal to P of B into P of A given B, or from this P of A and probability of A into probability of B given A. So among this, any formula can be used for P of A intersection B. If special case, that is A and B are independent, then P of A by B will become P of A. So P of B into P of A. Again here P of B by A, it will become P of B. So P of A into P of B. If special case A and B are independent, then P of A and B both to occur simultaneously is P of A into P of B. This is the multiplication law or rule. Hope this is clear for all of you. Now, few corollaries or conclusions from the earlier concepts. Suppose if P1 and P2 are the probabilities of success of two independent events, you have to note down, I have mentioned independent events, then probability that first event occurs and second event fails. So first event occurrence is P1 anyway we know. Second event fails. Second event failing means complement of the first event. In complement law we have mentioned when P probability of A complement is 1 minus probability of A success. Now success is P2. Its failure probability is 1 minus P2. So first event has to occur and is given. So into second has to fail. First event has to occur into second has to fail. So P1 into 1 minus P2. So probability that both events occur, both has to occur, first event and second event, both has to occur, or has to fail. So first event has to fail and means into second event also has to fail. So 1 minus P1 into 1 minus P2. So actually this both events fail means P of A complement intersection B complement. As independent events, A and B are independent means A complement and B complement are also independent. A complement and B are also independent. A and B complement are also independent. So any grouping will give independent events only. So we have already studied for two independent events when where intersection is given, then their answer will be multiplication of their probabilities. P of A complement is 1 minus P1. P of B complement is 1 minus P2. So into, as A complement and B complement will also be independent, then P of A complement intersection B complement will be 1 minus P1 into 1 minus P2. Okay. Now probability that at least one will occur. When at least one will occur, so probability total from total sample space probability. Sample space probability or universal set probability is always 1. From the total possibility of total sample space minus, what I am saying, at least one has to occur. That means either first one will occur or second one will occur or both one will occur. That means P1 union P2. I mean A union B. So when this equal to, from 10th class we can recall that A union B is nothing but universal set minus A intersection B complement, or in probability terms P of A union B will become 1 minus P of A complement intersection B complement. Okay. So actually either you can go like this or directly, simply it is very easy to understand. At least one has to, at least one has to occur means, here success is, the case is, if any one happens then it is success. If both are failure then only it is failed case. Here means if A is a success case, then P of A equals to 1 minus P of A complement. Just taking the terms this way, opposite way. So if we want success rate, from universal set probability we have to deduct the opposite case, failure case. For this failure case is when both the events are not occurring, that is the failure case. When both the events are not occurring, this is the probability. So when this probability is deducted from 1, we will get the success case, which is our desired one, at least one happens. So 1 minus P of A complement intersection B complement, which is equals to 1 minus of 1 minus P1 into 1 minus P2. Actually this is the answer. In another way, as I have earlier told, A union B equal to P of A plus P of B minus P of A intersection B, which is for A first event it is P1 plus for second event P2. For both the events, as it is independent, P of A intersection B will be P of A into P of B, means P1 into P2. So this is the answer. So you will see that if from the direct formula also, if we expand, we will get the same thing. 1 minus of 1 plus P1, minus P1 minus P2 plus P1 P2. So we take this everything from bracket, 1 and 1 will cancel, minus of minus, this is P1 plus P2 minus P1 P2, which is nothing but this one. So either you do it like this, at least one is given is union case, both is given intersection case. So at least one, either you go like this or you directly do like this, you will get the same answer. Hope the concept is clear. In probability, one of the favorite questions always asked is on deck or pack of cards. So in playing cards, there are generally standard playing cards, there are 52 cards, which are distributed into four orders. First one is hearts, diamonds, spades and clubs. In each of the order we have 13 cards. So total 13 into 4 is 52. Out of that, in hearts and diamonds, they are red in color. Red symbols are there, heart symbol and diamond symbol. In spades and clubs, they are in black colored, which is symbols I have given. In each set, the 13 cards are named as one ace card, which is shortcut A is given, ace card A. Next, numbering is 2, 3, 4. With numbers, it is there up to 10. This is 9 cards. This is 1 card. And one more is queen, king and jack. So it is Q, it is K, it is J. So these total are 3 cards. So 3 plus 9 plus 1, total 13 cards. So in each set, these 13 cards exists. So generally questions are asked within this. Okay. Now coming to next example, 2 cards are drawn in succession, means one after other, from a pack of 52 cards. Find the chance that first is king and second is queen. If the first card is replaced, first case, second case is not replaced. So in case 1, if first card is replaced, okay, and earlier I had described in 52 pack of cards how many kings are there total. Number of kings is 4. In hearts 1, in diamonds 1, in spades 1, club 1. Similarly, total number of queens is also 4. And total number of cards in total is 52. Okay. So, success in the first chance, if first time when we are taking, success rate for king to come is 4C1. Among these 4 king cards, either in diamonds or spades, clubs or whatever order it is, in that out of 4, 1 has to come. That is success rate is 4C1. Okay. Into remaining 4 queens are there. Actually, a question he is asking is P of probability of king to occur. First one is king and second one. So succession one after other when we are taking, king also has to occur, queen also has to occur, which is K intersection Q divided by total probability. Okay, so total is P of sample space. So P of sample space is nothing but 1. Now P of K intersection Q, probability of K, if K and Q are independent events, I already told that P of K intersection Q is P of K into P of Q. Okay. Since these are independent events, because king and queen are 2 different cards in any given pack of cards. In that, taking king does not affect the success of queen, taking queen does not affect the success of king. So they are independent of each other, so that's why intersection gives direct multiplication. So this is how it is. So for king to occur out of 4C1 chances, and for queen to occur as it is replaced, again probability that king occurs is 4C1 by 52 C1. Out of 52, 1 card we are drawing, that is the total possibilities, and our king requirement, so 4C1 into next time card is replaced, again we have 52 cards only, so total possibility is 52C1 only, but in the numerator, out of 4 queens we have to get 1 queen. So when we are drawing it, so first attempt, this is a second draw. So in first draw we are getting king, second draw we are getting queen. So which is equals to 4 by 52 into 4 by 52, which is equals to 1 by 13 into 1 by 13, which is equal to 1 by 169. Now second case, case 2, first card not replaced. Data is same here also, but when in first draw for king, probability P of K is 4C1 into 52C1. As once a card is drawn, it is not replaced. The remaining cards for the second draw is only 51 cards. So out of that 51, one we will draw, and for probability that that one card is queen is 4c1. So chances that the drawn card is queen is 4c1. So 4c1 by 51c1 is in the second draw probability that the card is queen. Probability that in first draw the card is king. So P of K intersection Q, which is 4 by 52 into 4 by 51. So it will give 13. So we can multiply and get the answer, which we will get as 4 by 663. Hope this sum is clear to all of you. Now next concept is a bit of important one. It is related to Bayes' theorem. So consider there are n number of events possible, the B1, B2, B3 and so on up to Bn. Out of that, in every element there is another element A which is dependent on these elements. This total is A only, everything is A only, everything. So this total part of this total sample space is A, and this is overlapping with B1 some part, B2 some part, and being dependent to some extent on B1, dependent on some extent to B2, B3, B, so on, Bn. So some fraction in every set. So these are dependent elements. Now when we want total probability of A to occur is, what we will do is simply add each segment of this part A. So when we consider in this part, how we will get is, this is nothing but of this total A, what is the intersection with this B1 part? That is P of A intersection B1. Similarly, now next this part. So this is P of plus P of A intersection B2 plus so on. Each part we will add. So that in short we can write integral sigma P of A intersection Bi, where I equal to 1 to n. So again we can write this as sigma I equal to 1 to n P of A intersection. As these are dependent, we can write them as P of Bi into P of A divided by Bi. Okay, so for B1, B2, B3 we will already know probabilities. Once this happens, in that what is the probability of A? I mean probability of A given Bi. So for each B1, B2, B3 everything when we add, I mean sigma, then we will get total probability of A. Now question is given that I want that A to happen from particular I, at I maybe say 1 or 2. So for example, let us fix as 2. Where I want this A to happen from 2 only, not from others. Then that probability P of B2 by A. I means I want A to happen, but A probability of A must happen, but that is from B2 only. I mean first I am deciding what to happen, then P2 must happen. So this one we already know, P of A intersection B2 divided by P of A, which is nothing but we will get P of B2 into P of A divided by B2 divided by this formula we will write sigma I equal to 1 to n P of Bi into P of A into Bi. Since it is B2, here it is B2. If it is B1, it will be B1. Whatever is. So if it is ith one, then this one also will be I. Or this say is R, Br, it will be Br. So R event, rth event. So this is how. This is the formula for Bayes' theorem. So let us solve one example on this. Now he has given a question. Urn 1 contains 5 red and 3 black balls. Urn you can consider an almirah or a box. Urn 1 contains 5 red. Urn 1 contains 5 red and 3 black balls. Urn 2 contains 3 red and 5 black balls. Urn 3 contains 5 white and 3 black balls. Now 3 balls are drawn at random from any one of the urns. He is not saying which urn. We can take from any urn. By closing our eyes, we just taking 3 balls. We don't know in which urn also we are keeping and we don't know which balls we are taking out. We are just taking 3 balls. He is giving that, he is telling if he is giving a condition, if those 3 balls that we are taking are red, I mean he is already giving that they are red, they are fixing it. Then find the probability that those 3 balls are from second urn, urn 2. Now here event A is getting red balls, picking red balls. So actually this can be done like this. This is urn 1, urn 2, urn 3. In every urn there are some balls. In that some are red, some are white, some are black. In that he is asking, already red is fixed. Then he is asking if it is red is fixed, what is the probability that that is from urn 2 only. So in the similar of Bayes theorem, so first, so B is urn, B1 is urn 1, B2 is urn 2, B3 is urn 3. That is the case. Then probability of what is saying, he is telling already red is given, A is fixed. Now that is has to be from urn 2, B2. So B2 given A is, from Bayes theorem we have P of, its reverse, B2 into P of A by B2 divided by C. If you want to remember it, conceptual wise you have to think. If you want to remember the formula wise, here he is asking, we have to understand which is A, which is B. That is must for anyone. Once we understand which is A and which is B1, B2, B3, if you want B2 by A, then from that B2 by A, in formula wise when we ask in numerator, B2 by A we will reverse A by B2, and whatever is denominator that will be B2. That we will write again. It is nothing but P of B2 intersection A. This intersection this divided by total probability of this denominator. Total probability of this means P of B2 intersection A plus P of B1 intersection A plus P of B3 intersection A, which we have already found. It's nothing but sigma I equal to 1 to n P of Bi into P of A by Bi. Okay. So from that we will get B2, probability of B2. Since it is a random experiment, we can pick balls from urn 1 or urn 2 or urn 3. We cannot, there is no preference. We have to take balls from 2 or 3 or 1. We can take from any of the others. So equally likely. When equally likely all 3 are having equal chances, probability of B1 equal to probability of B2 equal to probability of B3 equal to 1 by 3. Because choosing any one of them, that is 3C1. Okay. So total number of choosing is possibly, sorry, this is one only, sorry. Any one we are choosing among the 3. Sorry. So among the given number of bags, urns, we have only B. If we want B1, we have only one B1. If we want B2, we have only one B2. If we want B3, only one B3. So choosing one of them out of total number of bags, that is 3C1, which is 1 by 3. Okay. Now choosing P of A divided by B2. Or A divided by B1. A divided by B1. In B1, urn1 is fixed. In this, what is the probability that the 3 balls are from this end. So in this 5 total are there. Out of that 3 we have to choose. It is actually 1C1 here, 1C1 by 3C1. 5C3 divided by total number of possibility within R&B is 5 plus 3, 8C3. When we are taking, we can take any 3 of this total 8, but our success is red. So 3 must be red. 5C3 divided by 8C3. Similarly, P of A by B2 equal to, in B2, earn 3C3 divided by total 3 plus 5, 8C3. P of A divided by B3, here no red is there. So 0 divided by 8C3, which is equal to 0. Okay, hope that is clear. So since it is 0, we can neglect it. We have to consider only these two. When we substitute this in this formula, what we will get is P of B2 into A by B2. P of B2 is 1 by 3 into P of A by B2. A by B2. 3C3 is 1 divided by 8C3. Total divided by summation. This plus this plus this. So this into PB1 plus this into PB2 plus this into PB3. So PB1 is nothing but 1 by 3 into P of A by B1, which is 5C3 divided by 8C3 plus 1/3 into 3C3 divided by 8C3 plus that is 0, third one. So which will give the answer as 8C3. We have to find value of 8C3. I am having this. So 8 into 5 into 3 is 8 into 7 into 6 into 5 into 4 divided by, since 3 factorial is there, into 3 into 2 into 1 will be cancelled with 3 factorial, into 8 minus 3, which is 5 factorial, which is 5 into 4 into 3 into 2 into 1. So from this 8, 3 2s are 5 5. So it will give us 2 4s are 8 7s are 56. Right? So 8C3 is 56. So from this we will get it. And 5C3. 5C3 and 5C2 are same. 5 into 4 into 3 divided by 1 into 2. 2 2s are. 2 3s are 6 5s are. Sorry, something wrong. 5C3. Sorry, 5C3. So 5 into 4, 3 into 2 into 1 and 3 factorial will cancel. And into 5 minus 3 factorial, so 1 into 2. So 5 into 4. You can calculate, actually formulas are already earlier discussed already. So 5 to 0 is 10. So 5C3 is 10. So now if we substitute 1 by 3 and 1 by 56 divided by 1 by 3 into 10 by 56 plus 1 by 3 into 1 by 56. Denominators will be cancelling everywhere. Now remaining is 1 by 10 plus 1, which is 11. So this 1 by 11 is the answer for the given question. So probability that the drawn 3 balls are from urn 2 is 1 by 11.